Welcome everyone. In this video, we present our research on the localization of audio anomalies using the feature pyramid matching method. My name is Jorma Valjakka. I'm a master's student in computer science at University of Helsinki. The other writers of our paper are doctoral researchers Juha Mülleri, Lalli Myllyaho, and Juhani Kivimäki, in addition to Professor Jukka Nurminen. It's also worth noting that Juha Mülleri has additionally developed the discrepancy scaling method, which we utilize in our approach. Audio anomaly detection refers to identifying unusual or abnormal sounds within audio data. These sounds could be caused by different factors, such as background noise, equipment malfunction, or unexpected events. Anomaly localization refers to pinpointing the exact location or region within an audio sample where an anomaly appears. Information received from sounds can be helpful in many cases. For example, an experienced mechanic can often analyze car problems simply by listening to car sounds. Similarly, in the industrial sector, machines often provide acoustic clues when components begin to malfunction. Detecting these anomalies can help prevent potential damages. Unlike visual inspection, audio analysis does not require disassembling parts or stopping operation for visual inspection. This means the system can be monitored during operation, minimizing service interrupts. The same applies to medical examinations. For example, listening to lung sounds with a stethoscope can give the doctor valuable hints about how to proceed with the examinations. Precise localization of the anomaly can provide valuable information about the nature of the problem, leading to quicker and more efficient troubleshooting. Therefore, audio anomaly localization is not just about detecting the problem, it's also about gaining better understanding of the problem to take appropriate corrective measures. We introduce an approach for the localization of audio anomalies which employs the student-teacher feature pyramid matching, or STFPM method. STFPM has proven to be an effective method for locating anomalies in image data, the task which it was originally developed. Audio data is first transformed into images using the short-time Fourier transform, which creates spectrograms. Spectrograms are visual representations of audio that allows us to see the frequency content of audio signals over time. Spectrograms are used as inputs to the STFPM. The STFPM utilizes student-teacher model consisting of a pair of convolutional neural networks of identical architecture. The first CNN, known as teacher, is initialized with pre-trained weights and is frozen during the model's training. The second, the student, is initialized with random weights. The student is then trained on spectrograms without anomalies to mimic the activations of the teacher in the designated layers, subset of layers in the convolutional part of the network. During testing, the model compares the spectrogram of the test data with the learned normal patterns to detect and localize anomalies. If the input image is normal, the student will likely mimic the activation of the teacher well, leading to an array of small discrepancy values, and hence an anomaly with no large elements. However, if the input image is anomalous, some discrepancy values will likely to be large, as the student has not been trained to mimic the teacher on anomalous data. Regions with large values on the anomaly map should approximately overlap with the anomalies in the input image. To further enhance the accuracy of STFPM, we implement the discrepancy scaling method. This involves applying a student-teacher model to normal data to calculate the mean and standard deviation for each element in the 3D discrepancy arrays. These statistics are then used in inference to normalize the discrepancy arrays, improving the accuracy in both anomaly detection and location. What an advantage does our model offer? Firstly, flexibility. When creating a short-time Fourier transform, the selection of parameters can significantly influence how the model focuses its precision when locating anomalies. This allows for more detailed examination on certain acoustic features from the audio data that are particularly interesting. This adaptability means that our approach can be fine-tuned to the unique requirements of specific dataset or anomaly detection task. Secondly, our method offers efficiency. Once the model has been trained, the STFPM method demonstrates computational efficiency. This is especially valuable in real-world application where time is a critical factor when making decisions based on detecting and localizing anomalies. In our experiment, we created a set of samples containing synthetic anomalies placed randomly within two specific frequency ratings. These anomalies are mixed with authentic machine sounds and background noise at three different amplitude levels. In this way, we aim to imitate real situations where anomalies may occur in the combination of different sounds and noise levels. STFPM model was trained using sounds that did not include added anomalies. In our test, we observed models' performance with different frequencies and mixing levels, and the results are reported in Table 1 and Table 2. One of the objectives of the experiment is to compare how the results of spectrograms presented in linear and MEL scales differ from each other. This page shows the results of the linear scale spectrograms. We can notice that anomaly localization accuracy improves when the mixing level is higher. The louder sound naturally is easier to detect from the background noise. However, anomalies mixed at the quieter level still deliver reasonably good results, particularly in the higher frequency ranges. The MEL spectrogram uses the MEL scale to represent frequency. The MEL scale, designed for mimicked human hearing, provides more detail for lower frequencies compared to the linear scale. The use of the MEL spectrogram significantly improved the detection accuracy in the lower frequency range compared to linear spectrograms. Since linear scale spectrograms perform better in identifying high-frequency anomalies, the choice between the two depends on the frequency range of interest. Lastly, we have an example to illustrate our approach. The first image is a MEL spectrogram of audio sample with inserted sinusoidal anomalies in the 300 to 2500 Hz frequency range. The second image is the ground truth map of the anomalies, giving us the visual representation of where precisely these anomalies occur in the audio sample. The third image is the anomaly map generated by the STFPM. In the image, the areas corresponding to the inserted anomalies can be seen. The fourth image demonstrates the precision of our method and how it could be utilized. By applying specific thresholds to our STFPM anomaly map and overlaying it onto the original spectrogram, the inserted anomalies could be extracted. And this is the end of our presentation. We greatly appreciate your time and attention throughout this presentation. We are happy to discuss our research and answer any questions you may have. Thank you for watching.